we will discuss the similarity criteria, that how the similarity criteria can be utilized and what are the utility of those similarity criteria, because we have already gone through the dimensional analysis and the different type of problems associated with dimensional analysis. Now, we will see what is the importance of this similarity criteria in this such type of dimensional analysis. Why I am referring this dimensional analysis along with this similarity criteria, you will see the beauty of this similarity criteria in order to handle many practical problems of the fluid mechanics transfer and mass transfer. So, this is our fourth class on TP, TP4. So far as this dimensional analysis is concerned, so our topic for today is similarity criteria. So, the thing that you have learnt already, that an important use of dimensional analysis is that it can be made applicable the various sizes of a system. To different size of system, you can easily adopt this dimensional analysis. Why? There is, because of the fact there is no need of any external standard in such type of analysis. And if you are considering the characteristic dimension, that characteristic dimension may be there in the cylindrical system also, that may be there in the spherical system also, in the plane wall system also there is a characteristic distance. So, the dimension does not change irrespective of the fact that which type of characteristic dimension. Let us suppose in the case of the sphere, the radius may be treated as a characteristic distance. In the case of cylinder, the length and the diameter may be regarded as the characteristic dimension or characteristic distance, because any flow, either it is the heat flow or mass flow or momentum flow, may be there along with the radial direction as well as on the length direction of the cylindrical system, but both of them the dimension can be applied to any system size. So, if the dimension analysis can be applied to various system sizes, so it concludes into the fact that it is possible to design similar systems on industrial pilot scale plants as well as lab scale. So, on all these three scales you can easily design a system. So, the second question arises that if you are, let us take the example of a blast furnace. Let us take the example of blast furnace. The blast furnace is a very big structure, as you might many of you might have seen in the various steel plant. So, if you would like to design a blast furnace on a pilot scale plant, then you will take a smaller size. Then the question arises, can we choose those sizes in the arbitrary manner? No. Keeping the fact in view that the blast furnace is cylindrical in nature, so if you are designing two systems on different scale, one on the industrial scale, another on a pilot scale, so it is necessary to emphasize that the length by diameter ratio must be same in both the cases on the industrial scale as well as the pilot plant scale, failing to which any data that you have obtained on the prototype level may not be simulated on an industrial scale. And similarly on the live scale as well, you have to adopt the same ratio of the dimension, that is the length by diameter ratio, if you would like to prepare a model for a live scale blast furnace. So, hence for a system with respect to different scales, similarity criteria can be used. This is because of the fact that through a similarity analysis it is possible to extract the dimensionless number associated with that particular system and process, with that particular system and process therein. Okay, this is the meaning of similarity criteria. For systems having different scales, that dimensionless number has the same magnitude. That dimensionless number has the same magnitude. Have the same magnitude for all the scales. Okay. So, one of the important things which can be regarded as an advantage of the similarity criteria is you can easily obtain the dimensionless number which stands responsible for affecting the process, which plays a major role in order to dictate the entire process in a given system. That can be extracted, that can be decided, that can be evaluated, that can be framed using the similarity criteria. At the end of the class, I will cite you an example and I will do the necessary mathematical steps in order to establish this statement. Now, let us try to understand what do you mean by this similarity criteria. First, we should have an insight of this similarity criteria. Let us suppose I am considering these diagrams. See the different systems. These are the similar triangles, similar cylinders, similar system of forces. These two may be regarded as geometrically similar systems, is it not? Geometrically similar, that means if this triangle is similar to this triangle, then this side divided by this side should be equal to this side divided by this side, the normal principle of the similar triangles. In the case of the cylindrical system, the length divided by diameter for this cylinder, that is equal in magnitude with the length by diameter ratio for this smaller cylinder. So, such type of systems are regarded as geometrically similar systems. So far as the diagram number 3 is concerned, it is dynamically similar system. That means you are taking the two forces F1 and F2 which are acting over an object, and you are representing this F1 and F2 through the parallelogram law of force, and this is the resultant. Reducing F1 and F2 in some ratio, reducing these forces through some ratio, you are getting a slightly smaller version of this diagram F1 F2, but here again the resultant is F1 F2. So, that means F1 by this F1, that should be F2 by 2, or resultant this by this. So, such type of system is called dynamically similar system. Such type of system is called dynamically similar system. Dynamically similar system. So, as a matter of fact, geometric to dynamic, it is also called force similarity. Dynamic similarity can be made by defining dynamically similar systems satisfying the conditions as, take the ratio, let us x2 upon x1, this is equal to CL because you are considering a dynamically similar system. So, there should be the time ratio as well, this is called CT. Mass must be there in the dynamically similar system. So, M2 by M1, that is equal to Cm. X, P and M are the characteristic distance. T is the time elapsed, that means the time which has been consumed in order to travel that distance x, time elapsed, and masses of similar systems 1 and 2. So far as these constants are concerned, the CL, CT and Cm are the corresponding constants of proportionality. These are the corresponding constants of proportionality. Now if I am considering the dynamic inertial force on a moving object, also inertial force on a moving object can be given as force is equal to mass into acceleration, that is F is equal to m, acceleration is distance traveled divided by t square, mx by t square. So, F2 by F1, that may be regarded as m2 x2 divided by t2 square into 1 by F1, that is t1 square divided by m1 x1. So, it may be written as m2 upon m1 into x2 upon x1 into t1 by t2 whole square. Taking the help of equation number 1, this may be written as constant proportionality for the mass Cm, proportionality constant for this characteristic distance Cl divided by constant for the time elapsed, constant for the proportionality constant for the time elapsed. So, this may be represented as F2 by F1, that equals CMCL divided by CT square. That means on the basis of the equation number 1 that has been derived on the basis of geometric and force similarity. So, the basic fundamental is that the dynamic to geometrical similarity, this Cm by, this is the dynamic similarity, this is the geometrical similarity. These two similarity can be interrelated if you have an understanding of this similarity criteria. So, this above discussion can be concluded as above discussion concludes above discussion concludes that similarity criteria are a mean to express one system similar to other by providing the required conditions to do so. ठीक है, required conditions to do so. That means you can say the similarity criteria is a mean to provide those conditions by the virtue of which a particular system 1 can be treated similar to the system number 2. That means if you have designed an equipment on the industrial scale, the same equipment can be copied on a prototype scale by using the similarity criteria, and same equipment which I have used as a machinery in the industrial scale may be fabricated on a live scale by using the same similarity criteria. So, this is the meaning of the similarity criteria. So, as an example, the fixed length by diameter ratio may be regarded as a similar as a necessary condition for geometrical similarity with respect to a cylindrical system. That means if you are copying a blast furnace on a pilot plant scale, so L by D ratio for a blast furnace industrial scale, that should be equal to L by D ratio for a blast furnace for a pilot plant scale, and that should be equal to L by D for a blast furnace model for a live scale. So, you have to utilize this condition as a necessary and sufficient condition for copying the same object on 3 different scales. Now, come to the usefulness of the similarity criteria. Let us come to the usefulness of similarity criteria. Number 1, this does not require any external standard. It does not require any external standard. Number 2, since configuration of a system, can be defined as the ratio of magnitudes. It means because it is defined as ratio of magnitudes, so it means it is free of any measuring unit. So, you can say no measuring unit requires. These are the 2 important usefulness of the similarity criteria. So, next important thing is the state of similarity. What are the different kind of similarity that can be there during the similarity criteria analysis? So, I would like to emphasize those things now. States of similarity. State of similarity. States of similarity. First is the geometric similarity. Geometric similarity. The ratio of all corresponding lengths in model and prototype are same. This is the similarity this is the criteria regarding the geometrical similarity are same. When this condition pertains, that means a perfect geometrical similarity is existing between different scales. Second one is the kinematic similarity. Second one is the kinematic similarity. This is defined as ratio of all the corresponding velocities in model and prototype are same. This is the condition for kinematic similarity to happen. Third third one is the dynamic similarity. Third one is the dynamic similarity, ratio of all the forces in the model and prototype are same. An example, if the ratio of inertial force to viscous force, that means if I am observing that the ratio of inertial force divided by viscous force in the model, that is similar to the ratio of inertial force to viscous force, inertial force divided by viscous force in the prototype are equal. So, in that case a dynamic similarity can be assumed. Now, what is called this inertial force divided by viscous force, that is the Reynolds number. That means Reynolds number for the model, that should be equal to Reynolds number for the prototype. So, this is one of the conditions for dynamic similarity. Similarly, if if the Froude number for both the cases are same, then it is also called a dynamic similarity. If in the case of mass transfer, if the Schmidt number same for both the cases, then it is called again this dynamic similarity. Fourth one is the thermal similarity. Fourth one is the thermal similarity. This is defined as temperature gradients in two similar systems or because you are talking about the thermal similarity, so you can use the word reactors also, systems or reactors correspond to each other. This is called thermal similarity. Next one is the chemical similarity. Chemical similarity, a similarity criteria which is basically adopted by the chemical engineers, pharmaceutical engineers. This chemical similarity is defined as rate of a chemical reaction, at any time and location in the model that must be proportional to the rate of chemical reaction at corresponding time and location in the prototype, at corresponding time and location in the prototype. When such type of condition persists, that means if the rate of a chemical reaction at a particular time and location in the given reactor number 1 or given system number 1 must be proportional to the rate of the chemical reaction at the corresponding time and location, the reactor number 2 or system number 2 or the prototype, then such type of similarity is what is called as chemical similarity. These are the different type of states of similarity which is useful while you solve the numerical problems related with the dimension analysis, related with the similarity criteria, and also related with the physical modeling. So the important points regarding regarding the similarity criteria important points regarding similarity criteria. Number 1, kinematic plus mass plus thermal similarities this is equivalent to total similarity. When all these three similarities are satisfied separately, then it is called the total similarity, or it is also called as overall transport similarity. Transport similarity. This is the first important point regarding the similarity criteria, and the next important point is use of different similarity criteria. Use of different similarity criteria, it will conclude into the fact that the dimensionless number which stands responsible for affecting the process in the systems can be derived or can be obtained or can be decided. This is the most important aspect of the similarity criteria, that if you are using the similarity criteria with the reasonable accuracy and the reasonable scientific background, then it is possible to arrive at that particular dimensionless number which can affect the processes carrying out in the model, carrying out in the prototype, as well as in the lab scale equipment. The question rises, how? Now I will elaborate this point number 2 by giving an example. This is the last thing of the subject matter of today's class, that how this can be possible to arrive at the dimensionless number affecting that process through the similarity criteria. I will establish my statement through an example, and I would like to request to all you people to go through these numerical problems, such type of numerical problems which are of utmost importance for an engineers for during their respective industrial practices. So, example is, let us consider two rods, we are considering two rods, that is, the one rod is this and another rod is this. In both these two rods, the heat flow is taking place in the axial direction. Let us assume. Let us consider two rods 1 and 2. And unsteady state heat flow takes place in the axial directions of such rods, represented through the equation, the equation for the unsteady state heat flow, d by T1 d by small t1, that should be equal to alpha 1, the thermal diffusivity, d2 T1 by dx1 square. Let it be equation number 1. And for the second rod, d by T2 by this, that should equal alpha 2 okay. I am conducting the similarity criteria analysis for these two axial rods. Now, let us assume, let L1 and L2 are the lengths of two rods for corresponding points x1 and x2 on two rods. Okay. So we can write x1 upon x2, that should be equal to L1 upon L2, that is equal to CL. Let it be question number 3. Now, for thermal similarity to happen, two rods must have two rods must have same must have corresponding temperatures at corresponding times and location. Okay, corresponding times and location. Whether it should happen or not, two rods must have the corresponding temperature at two corresponding time at two corresponding location. So, we can write now for time correspondence, this T1 by T2, that should be equal to Ct. Let it be question number 4. Number 2, for temperature correspondence, this T1 by D2, that is equal to C capital T 5, question number 5, and for thermal diffusivity this is also equal, that should also correspond for thermal diffusivity alpha, this also corresponds to each other, C alpha by alpha 1 by alpha 2, that should be equal to C alpha. Now putting equation number 3 to 6 in the equation number 1 now. Now putting equations 3 to 6 in 1. Okay. Rewrite equation number 1 again first. Deva T1 by this, that should be equal to alpha 1 deva by deva x1 deva T1 by deva x1, or you can write deva T1 transform as per equation number 5 Ct T2 divided by deva Ct small t2, that should be equal to alpha 1, that is the C alpha alpha 2 deva by deva Cl x2, this quantity deva Ct T2 divided by deva Cl x2. Okay, or you can write Ct upon Ct, this, that should be equal to C alpha by Cl into Ct upon Cl deva 2 T2 divided by deva x2 2. Let it be question number 7. So here you can see all the quantity related with the temperature, time and the distance x, both with the suffix 2, is it not? That means equation number 7 stands responsible for describing the same process as the process that was going on in the system number 1. So for a full similarity to happen, if the whole similarity happens here, it means equation number 7 must correspond to the equation number 2. So you should write here that equations 7 and 2 need to be identical as per the similarity criteria or as per the similarity principle. Hence, comparing those equations, we can write what we should write, that this quantity, this coefficient, that must be equal to this coefficient. Okay, that means Ct upon Ct, that should be equal to C alpha upon Cl into Ct upon Cl. That is equal to C alpha Ct divided by Cl square, or you can say 1 upon Ct, that should be equal to C alpha upon Cl square. Better to say not to remove here, see, or you can say or T1 upon T2 into T2 upon T1, that should be equal to alpha 1 upon alpha 2. This Ct has a value T1 upon T2, is it not, into Cl square, 1 by Cl square, that means L1 square by L2 square, sorry, L2 square by L1 square, okay. Or you can write, this will get cancelled out, or you can write here alpha 2 T2 by L2 square, alpha 2 T2 divided by L2 square, that should be equal to alpha 1 T1 by L1 square. So we can write, so it concludes that the quantity alpha T by L square is same for both the systems. The question is, what this quantity is alpha T by L square? How we are regarding this as a dimensionless quantity? See, now alpha T by L square, that can be written as T upon L square by alpha. According to the principle of thermal diffusivity, this ratio can be defined as T is the time elapsed divided by this quantity is regarded as time required to heat the object to the steady state condition. Because of the fact that this ratio, this quantity corresponds to the ratio of two similar things, that is time, so it is called dimensionless time, or it is also called as Fourier number. This is the number which affects the unsteady state heat transfer, unsteady state heat transfer up to a larger extent. So, by the virtue of this dimensional analysis, we are able to know that the dimensionless number which is involved in the process is the Fourier number or dimensionless time that is defined as alpha t upon L square. So, this is the beauty of the dimensional and similarity analysis to arrive at the dimensionless number which stands responsible for affecting the process which is going on the two different systems. So, thank you students. In the next class we will go through the different dimensionless numbers involved in the similarity criteria and dimensionless analysis, and also we will try to study the different types of physical model which stands important for your semesters to come. You have a full course on the next semester, that is the modeling and simulation, and you will find much helpful for those courses to understand if you have gone through such type of things in an honest manner. Thank you.